Welcome to the channel, guys. Today we're going to be taking a look at IMO 2020 A7. So this is what the shortlist looks like. We have our A1, A2 all the way, and if we scroll all the way down, then our usual problem 3s and 6s on the actual test, on the actual IMO, would correspond to the shortlist difficulty around 5 and 6. But today, the problem we'll be looking at is A7. It's all the way down here. And as you can probably tell from how dark the red is, it's a very difficult problem, or it's supposed to be a very difficult problem. But don't worry, because we will be solving this problem together here today. And as it turns out, the problem doesn't really seem to be that hard, so I'm assuming it's probably just a relatively easier A7 that year. So anyways, the problem statement is quite short. It says that we have n and k are positive integers, and we're given a sequence of numbers of n numbers in the range 1 and to 2 to the k. And we wanted to prove that this sum is less than or equal to 4 root kn. And with all these sequences, we might think about induction, because if we can prove the case n minus 1 and then we can induct it to n, then we're literally done. And with sequences, we can often make use of the inductive hypothesis really well. But before that, I just want to write out the summation sign a bit, because I often find it kind of difficult to visualize the things in the summation, so I'm just going to write a few terms out to get a bit of intuition about this. And so we kind of want the sum to be really big, so that it's really close to the bound and we can get a good feel for things. But okay, we want the sum to be really big. What that means is that we want the numbers on the top, so like the A1, the A2, the AN, all of these things on the top, we want them to be really big. And the denominators, the things on the bottom, we want them to be small in order for the fractions to be big. So we want these red things to be small. And so if we think about it, for example, let's say we make A1 really big, then great, this term is really big. But then, for example, this fraction also gets really big, and since A1's in this fraction, also gets really big, and so all the denominators gets really big, including this one, all the way up to here. And that's not really good. We don't want that. We want the red ones to be small. But compare that to if we made AN really big, then great, this fraction is really big. And, well, by the way, this should be a squared. And you see AN actually only appears in the denominator here. It doesn't appear anywhere else. So it only affects the terms behind itself, which is none in this case. And so our natural intuition should be that the further back a term in the sequence is, the bigger we should make it, because it will affect less stuff. Okay, so following that intuition, we would later probably want to try to prove that this intuition is indeed true. But before that, let's take a look at some induction ideas. In particular, what do we want to induct on? Because there's n and k. If we induct on n, then we're adding a new term like an plus 1 squared over a1 squared plus plus an plus 1 squared. We're adding whatever this term is. But the thing is, this term can actually be quite big. For example, if I were to take this to be 2 to the k, and then let's say all the a1s to ans are 1. That's probably not the case, but if they're all 1s, then this thing is actually really small and this thing's really big. And if you try for yourself, the change here is not really big. And so our inductive hypothesis is actually not that useful in this case. So maybe we induct on k then. Let's see what happens when we induct on k. So when we do that, we're essentially just extending the range the variables can be in. And that's probably not going to change all of the terms that much, so it seems like it's a pretty good idea, because we can make the difference not too big. Okay, so let's explore induction a bit more by taking a look at the base case k equals 1. In this case, all the variables are in the range 1, 2. Let me just wall this off a bit. Okay, and so what we can do is actually we can apply the most trivial bound. So this sum which I'll write as I equals 1 to n of ai over a1 squared plus dot 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 plus ai squared. This sum, if we apply the most trivial bound, it should be at most, the top can at most be 1, and the bottom is at least 1 squared plus 1 squared plus all the way to there, and there should be a total of I ones, and so this should just be square root of I. Okay, so we've established this bound, and if we can show, by the way, this is less than or equal to this, and if we can show that this quantity is indeed less than or equal to 4 root kn, then we are done. So let me rewrite that. We want to show that the sum of 2 square root of I is less than or equal to 4 root kn. And this is a bit of intuition, which you'll gain once you do some more of these problems, but if you look at the sum, this actually reminds you a bit of integration. What I mean by that is if I were to, let's say, draw a plane here and let this be x, if I were to draw the function 2 over square root of x, so let's say f of x is equal to 2 over square root of x, it should look something like that. Well, it's obviously decreasing. And if I were to label these 1, 2, and I can kind of draw these rectangle things, and what they do is that, let me use a different color. So for example, if I take a look at this first rectangle, this width is 1, and the height is 2 over root 1. So this area, it's 2 over root 1. The second thing, similarly, the width is 1, the height is 2 over root 2, so this is 2 over root 2. And if I add all the way to 2 over root n, that's exactly what the sum is. So the sum is just the area of all these rectangles combined. So that's actually called a Riemann sum in calculus, and it's used to approximate the area under the curve. And so what's nice about this is that we can actually integrate this curve, and we will get an approximation, or actually the exact value of the area under the curve. And what I mean by that is, for example, if I were to color, let's say I color all these things green, then the blue area plus the green area is the area under the curve. And what is the area under the curve? The area under the curve is, if I were to integrate from 0 to n, the function 2 over root x dx, then if we do some calculus, the antiderivative should be 4 root x. Yeah, so this should be equal to 4 root n minus 4 root 0, which is equal to 4 root n. And guess what? Since k equals 1, this is just 4 root n. And so the blue area plus the green area is 4 root n, and since the green area is obviously positive, then the blue area must be at most 4 root n. And so this bound does indeed hold, and we have established our base case. Okay, that's really nice, and I'm going to erase all of this right now because we don't really have space. You know, I would love to keep this, but now we have established the base case, and we can see how we can try to induct. But before we do that, now we want to cycle back to the strand of intuition we previously had about the permutation of the variables. So maybe we can prove that the best case is when the variables are permuted in that way we talked about. So the bigger it is, the further back it is, the bigger it should be. And so how we can do that is, well, it's kind of formally called mixing variables. So for example, if I call this expression, if I call it a function f of a1, a2, an, then what I'm essentially saying is that, let me add a few more terms. Let's say we have ai, aj, an. Then what I'm essentially saying is that if aj was less than ai, then what I can do is I can just flip these two variables around, and then I would obtain a bigger expression. So f of a1, a2, aj dot 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 ai dot 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 an. Yeah. So what I'm saying is that if I flip these variables around, I should get a bigger thing. And so I don't need to worry about these cases because these cases are already covered by these other cases. And so I can only focus, or I only need to focus on the cases where the variables are indeed permuted that way. So this is called local refinement and also mixing variables because we are essentially just kind of breaking it down into a simple step. We want to show that this step does indeed work. It's called the mixing step. And then we can show that the most optimal case is indeed whatever this is. And so we only need to show that that is less than or equal to 4 root kn. Okay, so maybe we can work on proving this so-called mixing step. And what we can do is that instead of mixing random AJs and AIs, they're kind of far apart and unrelated. So what if I just mixed AJ and AJ plus 1? Well, if I could do that, then whenever we have the sequence, then I can just permute the adjacent terms, and eventually I'll get to a point where they are indeed ordered in ascending order, which is what we eventually want. Okay, so let's work on this. And the benefit of this is that all the other terms will be cancelled because, by the way, I'm assuming that AJ is less than, or AJ is greater than AJ plus 1. Yeah, so if this is the case, then we can indeed flip the variables around. And so for example, if I take a look at all these terms in the front, they cancel out. So they don't get changed by this permutation. And all the terms in the back also don't get changed because the two things flip, but then they're actually in there together, so it doesn't matter. And so the only thing that's changing is that originally I had AJ over square root of a1 squared plus dot 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 plus AJ squared plus AJ plus 1 over square root of a1 squared plus dot 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 plus AJ squared plus AJ plus 1 squared. And now I'm changing this to, I want to permute these two things, so I'm changing it to AJ plus 1 over square root of a1 squared plus dot 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 plus AJ plus 1 squared plus AJ over square root of a1 squared plus dot 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 plus AJ squared plus AJ plus 1 squared. Okay, so this is the only change. And if we can show that this change is an increase, it increases the total value of our function, then that's what we want. And because I don't want to write the sum of squares again, I'll assign them a variable name. Let's say x is equal to a1 squared plus dot 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 plus aj minus 1 squared. And so we want to prove that this is greater than or equal to this. This is less than or equal to this, or that this is greater than or equal to this. And we can, let's factorize this thing a bit, probably. So for example, I'm gonna move some terms over together. So let me take this term, which is aj over square root of x plus aj plus 1 squared. And then let's subtract it from this, which is aj and, okay, never mind, aj and square root of, this should be aj plus 1 plus aj square root of x plus aj squared plus aj plus 1 squared, and this is x plus aj, x plus aj squared. So this is one of our quantities, and the reason we're grouping them together is that they have this common term on the top, so maybe that'll help us out. And then we want to add this thing subtracted by this thing. So the top is aj plus 1, and then this right here should be square root of a1 squared, or we can just write x plus aj plus 1 squared. And the other one is aj plus 1, if I believe it should be, it's square root of x plus aj squared plus aj plus 1 squared. And we want to prove that this entire quantity is positive. And so let's see how, I can zoom out. Okay, so let's see how we can prove that this is positive. And the most obvious thing to do is to just cross multiply. So make the denominators common, and we can kind of see if that will work for us. So for example, if I were to do that, then this term, the bottom becomes something like x plus aj squared plus aj plus 1 squared. This thing multiplied by square root of x plus aj squared. And the top is aj. I can factorize out an aj here, and you would get something like x plus aj squared minus x plus aj squared plus aj, x plus aj squared plus aj plus 1 squared. Okay, it should be something like this. And then the other one is quite similar in that I'm going to take this out, and x plus aj squared plus aj plus 1 squared minus square root of x plus aj plus 1 squared. And we eventually want to use the fact that aj is greater than aj plus 1 to prove that this inequality is true. On the bottom, we have, I'm going to flip this order around so we can look at it more clearly to compare with that, because this first term is actually the same. We have over here is this. Okay, so what we're going to do is we're going to multiply each of these things by its, what do we call it? The conjugate, I guess? Okay, so for example, if I were to multiply this thing by its conjugate, which is the square root plus the other square root, then it becomes the base. You know, I'm kind of lazy. I'm just going to lasso select this. And then I'm going to copy and paste it over here. And then I'm going to, I'm just going to write the top part. And then the other thing is square root of x plus aj squared plus aj plus 1 squared plus the other square root, which is this thing. Okay, so the reason I multiply this is if we multiply this on the top, then what we'll get is just this square root squared, which is just the thing inside, minus the thing inside this. And if we look, the difference is just aj squared. So the top should just become aj plus 1 aj squared. And then similarly, we can do the same thing on the other side, and I'm going to write it subtract because this thing is greater than this thing. And I'm going to get the same denominator, which I'm going to again copy. Oops. I don't know why it looks so deformed, but anyways, we should get, I'm going to actually bring these things down here so it's a bit easier for us to see in a single page. This should be aj. And the other thing is this thing plus this thing, which is square root of x plus aj squared plus aj plus 1 squared minus square root of x plus aj squared. I believe that is correct. Yeah. And if we multiply it by its conjugate, we're just going to get aj squared. We're just going to get aj plus 1 squared because these two things cancel out. So what we should get is aj times aj plus 1 squared. And don't forget that we eventually want to prove that this thing is positive, this difference. So maybe we can do a direct comparison right here. Well, if we look at this numerator, we have that since aj is greater than aj plus 1, this numerator is greater than this numerator. I'm going to use red to denote the smaller thing. Yeah, the blue thing is greater than the red thing. And then we look on the bottom, I'm going to use green to denote same thing. So this is the same thing, this is the same thing. And we have that this thing, since aj plus 1 is smaller, this thing is smaller than this blue thing. And for example, this thing should be a plus right here. And we also know that this thing is smaller than this thing. So I'm going to give this a red and give this a blue. And in conclusion, the top part is bigger than this top part. The bottom part is smaller than this bottom part. Therefore, this entire fraction is bigger than this entire fraction. So it's the difference is indeed greater than or equal to 0. It is indeed non-negative. And so we have proved our mixing step, which is what we have set out to do in the first place, actually all the way back here. Yeah, so we proved the mixing step, and I'm going to remind us a bit about what the mixing step is, but that was clean. Anyways, our mixing step was just that if I have some permutation of the variables a1, a2, aj plus 1, an. If I have whatever this is, if I swap the places of these two terms, then our sum is actually not going to decrease. In most cases, it's going to increase. And so we only need to consider the cases where we have this thing is indeed in the right order. So if we keep swapping it, then we should eventually get that a1 is less than equal to a2 less than equal to less than equal to an. We should eventually get something like this, or indeed exactly this, because we can keep swapping it until the biggest things are on the furthest back, which is what we wanted in the first place. And so we only need to consider this case when the variables are permuted this way. We only need to consider this case. We don't need to consider any other case because they're all not going to be as optimal as this one. And we only need to prove that this is less than equal to 4 root kn for this case. And finally, we're going to do some induction with k now. So we've established the base case, we've established this permutation, and we're going to do induction now. Okay, so since they're ordered in this way, what I'm going to do is I'm going to define am to be the smallest index such that am is greater than or equal to 2 to the k minus 1. Or, actually I'm going to do this the other way. I'm going to make am the biggest index such that am is less than or equal to 2 to the k minus 1. And the reason I'm doing this is so we can apply our inductive hypothesis on the variable or on the cases of k minus 1. So for example, what we can do is we can partition our thing now into a1 over root a1 squared plus a2 over root a1 squared plus a2 squared plus plus am over a1 plus a1 squared plus plus am squared. Okay, I'm going to partition it into this first thing, and then the second thing, which I'm just going to write sigma now. I equals n plus 1 to n of ai over a1 squared plus plus ai squared. Okay, the reason I'm partitioning this is that I can now apply the inductive hypotheses to these first m terms. From the inductive hypothesis, on the k minus 1, we know that this, all the terms in this range are all the terms in here are in the range 1 to 2 to the k minus 1, so we can apply the inductive hypothesis, and this thing is indeed less than or equal to 4 times root k minus 1 m. Okay, so now we really literally don't need to care about any of this now. We only need to focus on this side. And what we can do is actually similar to what we did in the base case, because we can actually just apply the most trivial bound, which means that we're gonna use the bound that ai is less than or equal to 2 to the k, and each of these terms on the bottom, we're gonna use the fact that they are all at least 2 to the k minus 1, and also I'm going to absolutely forget about the terms a1 to am, so I only care about starting from am plus 1. So what we have is that this sum is less than or equal to 2 to the k over, and each time we're actually going to do how many terms are we going to have from m plus 1 to I? That's I minus m plus 1 and then plus 1. So that should be I minus m. Yeah, so we have I minus m terms down here, so we're going to take square root of I minus m, because we can always factor out this 2 to the k minus 1 squared, which under the square root is just 2 to the k minus 1. Okay, it should look something like this. And so we should have, this should be equal to 2 over, by the way, I need to write the sigma in again. Sigma I equals m plus 1 to n of 2 over root I minus m. And doesn't this look familiar, perhaps? Well, this looks exactly like the integration thing we just did earlier, and maybe we're guessing that we can do the same integration trick. So let's try that out. But you see, this time we have a minus m, but since m is a constant, maybe we can just incorporate that as part of the function. So let me draw a curve. Okay, let's call this curve f of x equals to 2 over square root of x minus m. And this time we also start at the point m plus 1 to the point n. Since we want upper bound, we're going to do the left Riemann sum. Or, I don't know if it's called the left or right. It always confuses me. Anyways, we should have something looking like this. And similarly, I'm going to color this blue, color this blue, color this blue. And whatever this is, I'm going to make it green. So this sum that we have is just the area of these rectangles. And the areas of the rectangles is less than, well, it's a strictly less than. But it doesn't really matter for our case, but it's strictly less than the integral from, now we're doing from m to n of the function 2 over square root of x minus m 2 over square root of x minus m dx. And if we were to find the antiderivative of this thing, I actually don't quite know what the antiderivative of this is, but we could try. It should look something like, for example, if I had square root of x, if I had 4 square root of x, the derivative should be something like 2 over square root of x. So maybe I just have 4 square root of x minus m. Okay, let's differentiate this. What is this? So, by the power rule, the derivative of this should be, first of all, 1 over 2 square root of x minus m, and then by the chain rule, we also need to multiply by 1, but that doesn't do anything. So, yeah, it is indeed 2 over square root of x minus m. Okay, so this is the antiderivative. Yay, we found it. And so now we can compute this integral, which should be equal to 4 over square root of n minus m, or sorry, our antiderivative is 4 times 4 square root of n minus m minus 4 square root of m minus m, and this is just 0. So it's just equal to 4 square root of n minus m. Hence, we can bound whatever this sum is from above by the quantity 4 square root of n minus m. And so all that is left, the only thing that is left is to check whether this holds true. This thing on the top, which we use the inductive hypothesis on, it's 4 times k minus 1m, plus this thing on the bottom is 4 times square root n minus m. We have obtained this upper bound to our expression, and we want to see if this can indeed be less than or equal to 4 square root of kn. If this holds true, then our inductive hypothesis can be used to prove our inductive step. Our inductive step is true, and so the entire problem is done. And we can first cancel out all these 4's, and actually this looks, by the way, this should be greater than or equal to, this looks a little bit like Cauchy-Schwarz. So actually it turns out it is exactly Cauchy-Schwarz. We can write this thing as k minus 1 times n minus 1 plus 1. Sorry, k minus 1 plus 1 times, let's do n minus m plus m. The reason I'm doing this is that I see these n minus m's, m's, and k minus 1, 1's, all these places. So by Cauchy-Schwarz, whatever this is supposed to be, wait, sorry, I reversed the sign again. Okay, this is meant to be less than or equal to. By Cauchy-Schwarz, this thing is greater than or equal to, let's multiply k minus 1 and m. So k minus 1 times m, the square root of this, plus the square root of 1 times n minus m, so square root of n minus m, is less than or equal to this thing squared. And recall that this is kn. Therefore, we have, if I take the square root on both sides, by Cauchy-Schwarz, we have square root of kn is less than or equal to square root of k minus 1 m plus square root of n minus m. And this thing, would you look at that? That is exactly what this is. Okay, so we are now completely done with the problem. And I'm just going to summarize everything a little bit. So the first thing we do is that when we look at this, we have the intuition that the bigger terms should be on the back, or the more further back a term is, the bigger it should be. And we prove that using what's called mixing variables or local refinement, but it just essentially just means that we optimize everything in their locality. So for example, if we permute two things, the sum actually gets more optimal. So we only need to consider this optimal case as opposed to all these other cases. So we first did that, and then using that we arrived at this condition right here, which can help us simplify a lot of stuff, because all this inductive step stuff we would not be able to do without the thing. And so the takeaway here is that you always want to make these observations and try to prove them. And the next thing is that we saw that there's sequences, and so that kind of hints towards induction. We prove the base case, and then we get something like this, and we want to see how we can use the inductive hypothesis to actually prove this inductive step. And we use the inductive hypothesis on this k-1 by grouping these terms that are less than 2 to the k-1 together to use the inductive hypothesis. And for the last part, it turns out we can actually just use some trivial bounds, and then we use some integration tricks to actually get an upper bound for this thing, which is 4 times square root of n minus n. And in the end, it turns out that these two things does indeed add up to be less than the bound, and the problem is therefore finished.